with Neptune raising concerns among analysts and space fans. Something similar well-known experts, including Neil deGrasse Tyson and Michio Kaku, have sounded alerts about the potential results of this imminent struggle. Yet how did Pluto end up on a collision course with its faraway neighbor? And what could this endless accident mean for us here on the planet? Could we explore this spreading-out event? Once remembered to be an unquestionable planet, Pluto was consequently renamed as a small planet as a result of its unique orbit. Regardless of this change, it continues to enchant and attract stargazers. Progressing estimates from indisputable specialists highlight a focusing area between Pluto's way and that of Neptune. These subject matter experts alert against a logical accident between the two planets, addressing a critical risk to Earth. Pluto's endeavor around the Sun is distinct due to its unparalleled characteristics within our planetary system. Its orbit ranges in width from 248 years. Since its discovery in 1930, Pluto still really can't complete a full orbit. Adding to its interest is the significantly bended state of its orbit, a departure from the practically indirect orbits of the major planets. Moreover, Pluto's orbit is skewed at 17 degrees to the ecliptic plane, advancing more extreme than various planets. One prominent piece of Pluto's orbit is its intersection point with Neptune's way. For around 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, opposing presumptions considering their specific circumstances in the Sun-centered system. So why hasn't a collision occurred between Pluto and Neptune? The explanation lies in the gravitational effects exerted by various planets. The appraisal of Pluto's orbit began not long after its discovery, presenting a baffling course for stargazers. As opposed to most of the planets whose orbits change fairly close to the ecliptic plane, Pluto's indisputable features include a grandiose inclination and a round shape. The mystery arises with the acknowledgement that Pluto's orbit crosses that of Neptune. The behavior of Pluto's orbit amidst these intricacies serves as evidence of the complexities inherent in space mechanics. The three-body problem in space involves sorting out the development and gravitational interactions among three eminent bodies, such as Pluto, Neptune, and the Sun. This issue explains the complicated exchange of their trajectories and gravitational forces. Terms like non-concurrent libration, scope libration, and the VZK influencing contribute to unraveling this heavenly puzzle. Astrophysicists insist that offbeat libration, which is responsible for keeping planets in their orbits, plays a major role in the context of Pluto and Neptune. This term implies that when Pluto meets Neptune's orbit, it is positioned at least 90 degrees away from Neptune, which is crucial for preventing potential collisions. Scope libration ensures that when Pluto approaches Neptune or other giant planets, it is oriented in such a way that it remains on their orbital plane, providing an extra layer of protection against crashes. The VZK influence explains why Pluto's orbit around the Sun appears astonishing yet remains stable over time. Despite apparent inconsistencies, numerical simulations in the late 1980s revealed that despite consistent properties, Pluto's orbit is indeed turbulent, with minor initial deviations leading to significant variations over millions of years. Nonetheless, Pluto's unusual orbit maintains stability over phenomenally extended timescales, keeping chaos in check. Continuous computer simulations have improved our understanding of how massive planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto's, adds to the security of Pluto's orbit. Similarly, Jupiter's massive gravity applies a significant influence, while Saturn's impact, though more subtle, also plays a role. Through intensive studies, scientists have shown that the combined effects of Neptune, Jupiter, and Saturn ensure the safe and stable advancement of Pluto in space for billions of years. These peculiarities are crucial for maintaining the control and consistency of cosmic dynamics in the universe. Without these factors, the solar system would be prone to greater chaos and instability, potentially leading to collisions or ejections from stable orbits, which could have increasingly growing effects on other celestial bodies. Understanding Pluto's orbit is particularly important amidst discussions about a potential collision with Neptune in the future. This data provides a clearer understanding of the unique nature of the neighboring planetary system. Pluto's case highlights how seemingly unstable orbits can achieve harmony through the complicated interaction of gravitational forces and orbital mechanics. Continuous observation and analysis of these phenomena are vital for gaining a better grasp of our place in the universe. Examining the depths of space frequently reveals the erratic nature of celestial bodies. Moreover, Pluto's orbit serves as an excellent illustration of this eccentricity. The nature of orbital chaos clearly demonstrates the sensitive dependence of a celestial body's path on its initial conditions, as shown in Pluto's case. Indeed, even slight variations in the planet's circumstance or speed can dramatically alter its long-term orbit. Simulations have been instrumental in helping analysts comprehend how Pluto moves in space. By making small changes in these simulations, astronomers can see how minor adjustments can have a significant impact. In the late 1980s, these simulations revealed an intriguing aspect of Pluto's path. In spite of features like non-concurrent libration and scope libration, adding to its stability, Pluto's orbit can still exhibit whimsical changes, as even slight variations in Pluto's circumstance or speed can lead to substantial changes in its trajectory over many years. Despite this inherent complexity, Pluto's orbit remains stable for an extraordinarily long time, maintaining coherence over billions of years. This suggests that beneath its apparently inconsistent appearance, Pluto's journey around the Sun follows a coordinated order, reflecting extraordinary events, especially with planets like Pluto that have unusual orbits. The inherent peculiarity of these structures makes long-term predictions uncertain. Numerical simulations help us understand and anticipate the future movements of celestial bodies. However, they also reveal the limitations of our predictions. These models heavily depend on precise initial conditions and replicate complex interactions. Even a slight miscalculation can lead to vastly different outcomes, making accurate predictions challenging. The chaotic nature of celestial orbits like Pluto's serves as a reminder of the ever-changing universe. While we've made progress in understanding space, Pluto's case highlights our continuously limited knowledge. The vastness of interstellar distances and the scarcity of planets in open space act as barriers against relentless collisions. Moreover, rogue planets are relatively rare compared to the number of stars and planets in stable orbits, making such encounters much more unlikely. Understanding the gravitational effects of giant planets on Pluto's orbit provides significant insights into the broader dynamics of the neighboring planetary system. It illustrates how each planet's presence and position can impact the stability and trajectory of other bodies within the system. Despite these complex forces, prominent astrophysicists are expressing concerns about a potential collision between Pluto and Neptune. This raises questions about why such an impact, which seems unlikely given these intricate dynamics, is still a subject of concern. Neil deGrasse Tyson, an eminent astrophysicist, offers a unique perspective on the intricacies of our neighboring planetary system, particularly regarding Pluto. Tyson, known for renaming Pluto as a small planet instead of a certain planet, shares insightful thoughts on how our understanding of cosmic mechanics is continually evolving. Tyson views Pluto's renaming not as a diminishment but rather as a necessary acknowledgement of our expanding knowledge about the diverse objects orbiting the Sun. His approach to celestial mechanics involves consistent learning and adaptation. He sees the complexities of orbits like Pluto's as a testament to the immense depth yet to be explored in space. Tyson believes that the allure of space makes astronomy so compelling. Furthermore, Tyson recognizes how space-related events and discoveries influence public interest in space science. He thinks occurrences like Pluto's renaming and its peculiar orbit provide opportunities to capture the public's imagination and curiosity about the universe. By discussing the dynamic and sometimes odd perspectives of celestial mechanics, Tyson aims to foster a deeper understanding and enthusiasm for the cosmos. Neil deGrasse Tyson opens a window for the general public to stand in awe of the wonders and mysteries of the universe. Working alongside other scientists, Tyson actively warns the public about the potential risk of Pluto's erratic orbit. After extensive analysis of Pluto, he has raised concerns that the three-body problem could pose a genuine threat, suggesting that a collision with Neptune is long overdue. Moreover, Tyson emphasizes how such an accident could disrupt the balance of the universe and lead to catastrophic results affecting Earth. A collision between Pluto and Neptune would be an extraordinary and alarming event in our neighboring planetary system. This impact could release a tremendous amount of energy, potentially obliterating Pluto due to its smaller size and cold composition. Debris from the collision could scatter across the solar system, posing potential risks to other planets and their moons. For Neptune, such an impact could potentially alter its atmosphere and orbit, depending on the specific details of the collision. Michio Kaku, a prominent theoretical physicist known for his work in string theory and scientific advancements, offers a fascinating perspective on this situation. His views on the possible fate of space exploration and the relationship between grand mechanics and theoretical physics provide valuable insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a brief exploration of the potential future of space exploration. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto, according to Kaku, can offer crucial insights for future space missions. This knowledge can help navigate the solar system more effectively, anticipating potential risks and planning missions to the outer reaches of our solar system and beyond. Kaku emphasizes that the models derived from studying Pluto's orbit can be applied to research other celestial bodies, providing a framework for approaching and understanding distant worlds. In analyzing the physical science of planets, Kaku frequently highlights the significant relationship between celestial mechanics and theoretical physics. He believes that the interactions and movements of planets, like the gravitational dance between Pluto and Neptune, are not isolated events but are connected to fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, aims to elucidate these principles at a fundamental level. He suggests that pondering the complexities of celestial mechanics, like Pluto's orbit, can yield insights into the essential laws of the universe. Like Tyson, Kaku has also expressed concerns about the potential collision, linking it to his theories about the universe. He believes that if Pluto and Neptune were to collide, it would be a critical event in space science, offering a striking observational opportunity that could potentially enhance our understanding of string theory. String theory, a theoretical framework that replaces point-like particles with one-dimensional strings, attempts to describe the fundamental forces and matter in the universe. The collision of such magnitude within the neighboring planetary system could create extraordinary conditions of energy and gravity, providing insights into the behavior of fundamental particles and forces under extreme conditions. A key focus in string theory, moreover, the gravitational waves generated by the collision could provide significant data for testing assumptions related to string theory, gravity, and spacetime. While the immediate impact on Earth would be negligible due to our distance from the outer neighboring planetary system, the far-reaching consequences of such an event could be profound, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and various fields of theoretical physics. Pluto's orbit serves as a striking illustration of celestial mechanics, demonstrating both stability and chaos within our neighboring planetary system. The extraordinary characteristics of its orbit are influenced by the gravitational forces of nearby planets, particularly Neptune, highlighting the complicated and dynamic nature of space. The universe holds many secrets, and the three-body problem is just one of them. There are other potential calamities that scientists anticipate. While the possible outcomes of planets colliding in space are extremely low, it is not entirely implausible. The way planetary orbits are influenced by various factors, including gravitational interactions, is understood through the lens of the three-body problem. In some space systems, like TRAPPIST-1, with 7 Earth-sized planets, gravitational forces create a rhythmic configuration driven by orbital resonances. Over time, these patterns can make planetary orbits less stable, potentially leading to collisions. Despite the crowded nature of systems like TRAPPIST-1, collisions are not currently occurring. Scientists eagerly monitor these systems to understand how planets affect each other's orbits, especially when they are in close proximity. This knowledge helps us appreciate the evolution of planets in space. Rogue planets drifting through space without orbiting a star present an additional unpredictable element. These planets, once part of a star system, are expelled due to gravitational disturbances or other cosmic events, such as the nearby passage of another star or dynamic instability in other systems. Over time, these wandering planets can traverse vast distances, possibly arriving at regions far from their origin during their solitary journey. There is a chance of them encountering other star systems. If one of these rogue planets enters another nearby planetary system, there is a slight possibility of a collision with a planet in that system. However, given the vast and overwhelmingly empty nature of space, the likelihood of a rogue planet directly impacting another planet is quite low.